This lecture is on hydroboration oxidation. It's one of the last reactions that we'll talk about with alkenes. And it's very special in how it operates with regard to mechanism. It's definitely something different than we've seen before. The reaction with its conditions is right here. These conditions look a little complicated at first. The major bond formation that controls the regiochemistry and the stereochemistry is all with this boron reagent. Now it's simply just BH3, that's an sp2 hybridized boron. It violates the octet rule, there's only 6 electrons around it. And actually that electron deficiency controls how boron's going to react. And it makes it do things that are quite different. In this example we see we have an alkene, and that alkene becomes an alcohol. So this is essentially the same kind of product that we observe with hydration reactions. We've replaced the pi bond with essentially a molecule of water, an OH group and an H. However, how this operates is quite different than hydration. Notice, the OH group goes to the less substituted carbon, and the H goes to the more substituted carbon. That's anti-Markarnikov regiochemistry. So boron behaves very differently than anything we've seen before. We can designate this anti-Markarnikov regiochem by just saying that the hydrogen bonds to the more substituted alkene carbon, which is counter to what we see with normal hydration. Stereochem of the reaction we'll look at in a minute, but you can write that down in your notes and we'll have plenty of examples that go through that. The other reagents here, hydrogen peroxide and sodium hydroxide, we're already familiar with. In the mechanism, I'll show how those operate. When BH3 interacts with the alkene, it actually breaks that pi bond and you'll form a boron-carbon bond initially. And so we can designate this by showing the approach of the boron. And so I'm going to draw BH3 like this, where I've highlighted one of the boron-hydrogen bonds. What gives this anti-Markarnikov regiochemistry is the fact that boron, with its 2 hydrogens here, is a bulkier group than just a hydrogen atom. And so the boron group will selectively choose to interact with the less substituted carbon. The hydrogen will approach the more substituted carbon. As these approach, essentially the electrons from the pi bond and the boron-hydrogen bond rearrange. One set of these electrons essentially will go to form a carbon-hydrogen bond. The other set of electrons from the boron-hydrogen bond can go to form a carbon-boron bond. Now we can't necessarily keep track of these electrons. These arrows could be drawn the opposite way. But one of them will form the carbon-hydrogen bond, one will form the carbon-boron bond. The results of this action break the boron-hydrogen bond and give us our new bonds here in this intermediate. Because the boron-hydrogen bond is intact on its approach to the alkene, they must come from the same side. And this gets into this stereochemistry of the reaction, what's called a syn addition. And so previously, in looking at many of the reactions in this chapter, we've observed anti-additions, but this is different. What happens next is now these reagents are added into solution. The hydrogen peroxide first will oxidize these boron bonds, and basically an oxygen just gets inserted in there. There is no official mechanism for this. It's complicated oxidation chemistry, so we won't draw any more electron arrows. But essentially we get an oxygen inserted in between the carbon-boron bond. And also, into these boron-hydrogen bonds. Effectively, what this does is makes this more stable. For the boron, it has more electron density around it. But this won't last long. We can see in our product, we just have that carbon-oxygen bond. The last step is just cleaving off this boron piece. So the hydroxide from the sodium hydroxide then will actually come in and attack boron. And so the stereochemistry here is unchanged. The oxygen bonded to that carbon will be the same oxygen we see up in the product. And so the final product appears here. We don't need to show the electrons. What is important in this mechanism is just this first step, because it defines both the regiochemistry and the stereochemistry that we observe in the product. How boron goes on there, effectively where it is in three-dimensional space, is exactly where the OH group will come and take its place. So that part's easy, there's no change. What is useful to look at is what the transition state would look at from this picture here. And just to give a little more room, I want to draw the transition state in. Maybe you'll draw it beneath in your notes so it's not so cluttered. But the transition state then, it's going to be a four-membered ring intermediate where bonds are breaking and forming at the same time. And so this four-membered ring, which is mostly planar, also illustrates how that syn addition has to occur. Boron and hydrogen must come from the same side of the molecule. We can look at some other examples to go over these same characteristics. It's important to write down all of the reagents every time. When we look at this product, we've got an unsymmetrical alkene. And so one of the sides is definitely more sterically hindered than the other. And so we can predict a product using what we know about boron chemistry. I like to start with predicting products, just drawing the alkane skeleton. We won't see any rearrangements with boron. And so we know the pi bond's gone. Now we just have to think, where does the boron go that's ultimately replaced with the OH? Well, it'll go to the less substituted carbon. The hydrogen will go to the more substituted carbon. And we can draw those in. But when you do draw those in, it's important to remember they have to be on the same face of the molecule. And this is probably the easiest way to represent that in this example. Since this boron compound can come down from the front of the board or from behind, we'll get a mixture of enantiomers. Just like before, anytime we've created a stereocenter, and here we've created two stereocenters, anytime you create a stereocenter, you'll get a mixture of enantiomers. And so we'll get exactly these two. Both of them, again, show that syn addition. The hydrogen and the oxygen are on the same side of the molecule, and that has to be. Here's one to try on your own. Take a minute and see what you get if you predict the products here. what you should get is this mixture of enantiomers. The hydrogen went to the more substituted carbon, the OH goes to the less substituted carbon. What's tricky when you draw these groups in, the end result is that the OH must be trans to the methyl group because it has to be on the same side of the molecule, or cis, to the hydrogen that it added on with. And so both is the case here. Again, we've got now two stereocenters we created. We get a mixture of enantiomers. Now what I want you to try and do is take this molecule, again an unsymmetrical alkene, and react it with our boron conditions, or hydroboration, and with our old conditions, hydration. And while you're working on that, you can investigate the product here as well. And so think about the difference between these two conditions. This effectively is going to give us access to more than one alcohol from the same alkene starting material. So it's very useful for synthesis to have two different methods. If I first look at this one over here, we end up with a tertiary alcohol. Markarnikov addition. If we look at this example right here, we'll get the Markarnikov product and an anti-Markarnikov product. Since we're not reacting at this stereocenter, it will not change. If the boron approaches from this face of the molecule, the bottom side, we'll end up with this specific enantiomer. If the boron reagent approached from the front face of the molecule, we would end up with this specific stereoisomer. Initially I said enantiomers, since we have this chiral center that's not changing in the product, these would be a pair of diastereomers. But these would be the only two possibilities you could get. With H3O plus here, we could have potentially this isomer, again, Markarnikov addition. The other hydrogen went down to this spot. We don't need to draw it in there. This is a tertiary alcohol. There's no rearrangement that would occur because it wouldn't benefit it. And you can work through that mechanism to see that. Or you could get the other stereoisomer, or diastereomer in this case. Notice in both of these reactions, since you're not reacting at the chiral center that's there initially in the molecule, and you don't create that chiral center, its stereochemistry is maintained. The stereocenters that you've created in the reaction, those can go either way, and you get a mixture. The last thing to talk about with boron chemistry are some other reagents that you might come across. Basically, anything with a boron-hydrogen bond is going to do the same reaction, and they react with carbon-carbon pi bonds. Some of them are better than others in specific instances. One of these reagents is called 9-BBN. What 9-BBN is an 8-carbon ring, so it looks like a stop sign. And then if we number our ring, between carbon 1 and 5, kind of up top here, hanging over the center, is a boron atom. And so it's bonded to these 2 carbons. With that boron is a single hydrogen. So this is a really bulky cyclic molecule with a bridging boron over the top. It's much, much bulkier. It'll be very much more selective for the less hindered carbon of an alkene. It makes it harder to draw the mechanism, and mostly everything is true with BH3. Sometimes you can get mixtures of products with BH3 because it's pretty small, but with this one you'll definitely obtain a single isomer. So this is called 9-BBN. We can represent its structure three-dimensionally. So this is like a chair conformation, only you've got 8 carbons in the ring. But so the actual three-dimensional structure looks more like this. If we want to do an example reaction with 9-BBN, the conditions are exactly the same. Say, for example, we have this molecule. We can react with 9-BBN, followed by peroxide and hydroxide. And you end up with the same product. It's an anti-Markarnikov regiochemistry and a syn addition. So this, for us, is effectively interchangeable with BH3. They do the same thing. And there's many reagents like this. This just gives you an idea of one of them.